Hello. So this is the last section of the chapter 22. In this video, I'm gonna talk about electric potential energy and electric potential. So they're little two different things, okay? Um, so far, what we have done was we learned about electric force. Anytime you have two charges, you're gonna have electric force. And we also learn about the electric field. You have a one charge, and this charge, just having a charge, you create the electric field. So therefore, when you bring another charge nearby, then this charge feel the electric field created by the another one, and you feel the force. So force equals Q of the charge times electric field created by this charge. This charge can be a multiple charges here, right? That has the unique electric field created by multiple charges. You simply just add all the electric field on top of each other. And then you bring another charge, and this charge feel the force because of the electric field that's uniquely created by this configuration. So that's the electric field and electric force, all right? But okay, you bring a charge in and then it has a force. What's that? You move the charge in while feeling the force. So you have a, I should have a big charge. Let's say I have a big Q here, positive. So I have a big Q here. And then I bring a small q like this, right? The small q nearby, right? And then by having this q, big Q here, it's creating an electric field. And then I'm bringing this little q. That means I'm doing a work is required, because if they're both positive, let's say, then there's going to be a force on this little q here that feels a repulsive force. So even against the repulsive force, I'm bringing it closer, right? Against the repulsive force. So I'm doing some work. There's a work done. Force times distance equals work. Work equals force times distance, right? So whenever you do something, you move, you displace something against the force or along with the force, there's a work that's done. Work is change in energy, right? So whenever you have some kind of work done, that means you change energy. Imagine, I have this positive Q here and a big Q here, right? And then by being here at this location, this position, this is right now in the electric field that's created by this. And if I let go, what happened to this little Q? It's going to move out, right? So being here, this energy at this location will be converted into kinetic energy. There's a work done by there's a virtue of being here, this location in the field. So anytime you have a charge in the field, that means you have electric potential energy, because you're going to have a force. Then you let go, this charge is going to move. It's almost like a spring, right? You either compress the spring or stretch the spring, right? If you compress it at that location, there's elastic potential energy. And then you let go, it's going to go outward. And then if I'm stretching it, then it wants to go backward. So the potential energy converts to kinetic energy. So the location, the length of the spring has, if you're doing the force, because there's elastic force, and you have some potential energy. In this case, it's the electric potential energy. You're going to have electric potential energy. I can show you Why don't I show you in note here? So I'm going to share the note here. Okay, chapter 22. And I'm talking about discussing electro potential energy. So let's say this is UEL, okay? Imagine what we know. This is Earth, Earth, so the ground, and then you have an apple. This apple has a gravitational force downward, Fg, and then let's say if you bring the height h above, there is at this location, this apple possess gravitational potential energy at this location, UG, right? Let's see, I have a big Q, positive big Q. And I could have a positive, but let's make it negative little q. Negative little q. Then there is a force between this minus q and a positive q, Fe, right? So being here at this location, D, from it, there is, remember, so this big Q, let's see, this big Q is this big Q is, having the electric field lines like this way, right? That. And then because it's negative, it turns into the opposite direction. The force will be the opposite direction. But anyhow, so the force, this force is equals to QE, and then because this is negative, so it flips, the direction flips. So then there is an electric force on this little q, negative q, and then what happened? If you let go, this is going to move down, just like apple moves down to the ground. So there is UEL, the electric at this location, being here, just staying in the field. This little cube possesses electropotential energy. Electric potential energy. I'm sorry. Electric potential energy for being in that location, because this UEL will convert into kinetic energy. If you do, so let's say if you do a work against electric field, what happened to the electric potential energy? If you do the work against, so in that case, you do it against it. So you're putting up this minus q higher, farther away in this case. That's because the electric field line is coming out radially outward, but then the force is going to be towards it. So you're going to move it away. Or you can think about it like another case example will be you have a big Q and then you have a positive Q. So you're going to move it towards, if you move it towards D, or you could have a positive Q and this is minus Q, then you move it away, D. This is going to be the work, you're doing the work against electric field, right? What happens to the potential energy? If you do it against the work, electric field, that means you have a, just like the apple, right? You do it against it. So you move the apple higher against the gravitational force, then you have an increase in potential energy. You do, because it has a more potential to do the bigger work by you bringing up higher. Same thing happens if you move the little charge against the electric field, then it has a potential to do more work. So you have a increase. That's how you can increase in uh, electric potential energy. So electric potential energy, and then if you do it along with the force, electric force, along with the electric force, then you have a decrease in electric potential energy, right? So electric potential energy, electric potential L is what it is the energy that the charged particle possess um, by virtue of its location in an electric field. And we use, because it's a potential energy, we use the same unit, it's a joule. It can be positive or negative. Same thing as a gravitational energy, but change in a potential energy means something. Absolute value of a potential energy, again, it doesn't have any value to it. It doesn't have any physical value to it. Or you just have a value. But change in potential energy is the one that's we're interested. Do you have an increase in potential energy by how much, or decrease in potential energy by how much? But you can put zero anywhere. And typically for the electric potential energy, we put zero at infinity. So you imagine like, oh, you're bringing this charge from very, very far away, the infinity. So where it almost have a zero effect of electric field. And so electric field never dies. Um, the electric field lines that are usual, they never cross with another electric field lines. And also it continues indefinitely. So technically, you're going to have an electric field lines infinitely, but you're going to see that it's very, 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 very small. It's almost zero. So that's why we tend to put the electric potential energy starting from infinite point. That's a typical thing, but you don't have to. There is no such a rule that where the electric potential energy has to be zero. All we care is how much it's changed from one location to another location. change in potential energy has some physical value to it. So that's it. That's the electric potential energy. I can show you the graph here, the slide. Let's see. Here. So you see, this is electric potential energy, right? If you have a pillar and then it's suspended by the rope, being up high, it has higher gravitational potential energy. And then when it's cut, the gravitational potential energy will be converted into kinetic energy. So the loss of a gravitational potential energy is going to be the increase in kinetic energy. On figure B next to it, instead you have a big negative ball underneath and you have a positive test charge up there. The positive charge up there has a electric force that's attractive. So this positive one wants to go down to negative, but it's being supported by the rope again. When you cut the rope, then this positive charge from that location wants to go down. So the energy is converted into kinetic energy. So being there, you have some electric potential energy. Then you lose the electric potential energy as it's attracted towards the negative and then converts into a kinetic energy. All right? You have an increase in kinetic energy. And also to have the little positive one in a negative charge, in the field that's created by negative charge, you have to do work to be there. Work is required to be in that location. So, and you need to, work is done or either lost or increased, positive or negative, when you move it in the electric field. So when you move the charge in electric field, every time you have a work done, and if you have a change in, then you have a change in potential energy. Similar thing, this is comparison with spring, elastic force, right? If you compress it, you have a force. But when you have a big charge and then a little charge here, they feel repulsive. So to push it towards the big charge, positive and positive, it requires some work. You're doing a force is outward, and then you're doing the work against the force. So you're increasing, is that increase or decreasing potential energy? If I'm doing, so positive and positive, outward, right? So this is a little charge, big charge here, and then a little charge here. This little charge have a repulsive force. They're both positive, let's say. And then you're doing, you're pushing it against the force. So do you have an increase in electric potential energy or decrease in potential energy by moving it from this to this, closer? Increase in electric potential energy because you're doing the work against the force, right? Okay, so something like that. You can think about it similar to the spring force or gravitational potential energy, very similarly. But because of the field and the force, if you have a charge in the field, you also have electric potential energy. Isn't that fun? Like all the stuff you learned, and you can apply it here. Okay. So that's electric potential energy. Let's talk about electric potential. Okay. So we have gardeners coming and mowing the lawn. Hope it's not too loud for you. Sorry about that. So let me share the screen. Back again. Okay, so let's see. Oops, what happened? Um, Hopefully it's not as loud now. Now I'm going to talk about electric potential. Okay, electric potential. Looks a little bit darker. Oops, here. So we said electric potential energy, and then it's very confusing because of the naming just seems similar. That the reason why one is electric potential energy, the other one is electric potential. You're going to see it, but electric potential is somewhat that we see more often in our daily life. And so here it is, electric potential. Just I'm going to go dive into the definition of electric potential. Electric potential. Sorry about all this noise. Electric potential equals to electric potential energy that we just learned, energy divided by the unit charge. And we have a new unit that's called volt. You know, the 12 volts, 110 volts that we hear, that volt. It's a scalar. It could be positive or negative, just like electrical potential energy. It could be zero, positive, negative, um, and yeah. So, but it doesn't have any information about direction, just the magnitude. So it's a scalar. So 1 volt, you can see 1 volt. 1 volt is equals to 1 joule of electric potential energy divided by the coulomb. 1 volt is equals to 1 joule per coulomb. That's just what it means. So let me see. I can show you the. Why don't I show you the slide too? Here. Okay, electric potential, which is voltage, not the potential energy, is energy per charge. So how much you could have potential energy if you were to put that charge over there. That's the idea. How much energy? So you're gonna, so just like an electric field, right? There is an electric field created by the big charge, and you don't feel anything until you put the little charge or whatever the test charge that you're interested in, right? Then you feel force. Same thing with the electric potential. There is an electric potential created by the charge or whatever, the environment. And then you're going to have electric potential energy if you put that little charge over there in that environment. But even though you don't have that, we can say that there's going to be this much voltage at this location. And therefore, if you add your device, electric device or electric potential, electric charge there, then you can say, oh, you're going to have this much potential energy. All right, that's the idea of electric potential. You're going to have the environment has electric potential, voltage created. And then you bring the device or electric charge, then you get to have a potential energy. You're doing some work. You can do some work. But before that, there's no potential energy. All right. So in equation form, it says electric potential equals electric potential energy per some kind of amount of charge, which could be the amount of charge that you need in your electronic device, or it could be just the charge you're looking at. That's the definition of a voltage, electric potential. So here, electric potential is measured in joules. Electric potential, on the other hand, is measured in A, volts, B, watts, C, amperes, D, also in joules. You should know how to do it. All right, so that's the voltage. Let's come back here. Let me go into the whiteboard screen again. Okay, so let's share that one here. All right, so this is the definition of electric potential. Imagine you have a, so here, imagine you have a Q, big Q. So there are three cases. You have this big Q here. At the same location, away, um, away from this big Q in the same location. So here, it's same distance, D. Same distance, D. I am going to bring the little Q naught here. And in this case, I'm going to bring the 2Q naught here. And in the third case, I'm going to bring 3Q naught here. Okay? So environment is identical for the case 1, Q naught, 2Q naught, and 3Q naught. It just depends on what kind of a charge you're bringing it at that same location. So what would be the electric potential energy? Electric potential energy for the Q naught, right? So that is electric potential energy. What is that? That's UEL. And that's in joule. And then what would be the electric potential? V. Let me see. Volts. So let's say that electric potential energy for the Q naught in the first case is U naught. And then electric potential, the volts at that location is V naught. What happens if it's in the same location, but now I change that Q naught to be 2Q naught? What happens to the electric potential energy? And what happens to the electric potential? If I change to 3Q naught, what happens to the electric potential energy? And what happens to the electric potential or the voltage? All right. Maybe I can leave this in a discussion, or should I do it? I will do it. So the answer is um, when you have a 2 charge, 2Q naught, then electric potential energy will be doubled. Just like if you increase the mass to be double the mass, right? You have a more gravitational potential energy because you have a more potential of doing the work. So what's the 3Q naught? You're going to have a 3Q naught, 3 times more potential energy. But potential, electric potential, which is the volts, it just doesn't matter what you have. It's just environment created by this big Q, big positive Q here, this one, right? It's due to here that virtue of being in that location. So even though you bring a 2Q naught or 3Q naught, the voltage created by the big Q stays the same. It only depends on the distance from the big Q. So the voltage is higher when you're closer to the big Q and lower when you're farther away. And the potential energy depends on what you have, what kind of a charge you have. But we can say that closer to the big Q, you're going to have a bigger voltage. Because if you were to bring something, you're going to have bigger potential energy. Why do we want to do this? Why do we want to have a voltage? Imagine, let's stop sharing. So why do we have a voltage? What's the voltage is about, right? Imagine, so what's the voltage that's coming out from your wall? Or let's say the battery. I don't have the battery. Hold on for a second. I'll stop it for a moment. All right, so I stopped and to get a battery. So what's the voltage that's coming out from the wall? That's 110 volts. It's actually AC, but 110 volts, right? Um, it's no matter what I connect to it, it's 110 volts. So let's say I need to connect a hair dryer, or I want to use this computer, right? I want to use the phone. I want to use the um, iPad. They all use a different amount of work. They do different amount of work either way, right? So they need different. They use a wattage, different wattage. What's the power is equals to work per time. So they do different amount of work depends on the electronic device. But regardless of what electronic device you connect to the wall, it's 110 volts, right? So we don't really have it's that's what the voltage means. You bring the electronic device, then you're going to have some kind of a work done. You don't feel anything until you bring the electronic device. It's just have 110 volts. Until you touch it, then there's a work done on the conductive water that we have inside, then work will be done. But if I don't touch it, there's just 110 volts. Touch it, then finally the work is done. Touch it, then finally work is done with the electronic device. Then you do some work. But otherwise, it's just 110 volts, whatever you connect. Same thing happens with this battery here, right? This battery says how much? What's the voltage? 1.5 volts. That low? Yeah. So this is a 1.5 volts battery. But does the battery voltage changes? Depends on I connect a little light or I connect it into the mouse, or if I change electronic device, does 1.5 volts will change? No, it's always 1.5 volts. Whatever that I connect, and then you do different amount of work. So you have a different potential energy that depends on what you're connecting to it. But this one ensures 1.5 volt. It's actually the potential difference. We're going to talk about that difference in potential. But anyway, but this one assures the 1.5 volt all the time. The wall, it's not all the time. It fluctuates quite a bit, but 110 volts. That's what's assuring. So you can connect any charge, but it's always 110 volts or 1.5 volts or 9 volts battery. You see, so that's what the electric voltage is about. It's just you have the electric voltage created by the charges in it, and then you bring another charge, then you feel the force, and then you do some work. You do have a potential energy that you can do kinetic energy. It can convert it to kinetic energy or other mechanical energy. All right, that's the idea of field and voltage. So then I want to show you one more thing about the field, electric field and the voltage. Let's see, I'm going to go back to the screen again. Right? So let's say we said that if you have a positive Q, electric field line is coming out radially outward. And depends on the charge, number of lines can be changed to be more or less. Electric voltage depends on the distance from the electric charge. Closer to the electric charge, you have a higher voltage. Farther away, you have a lower voltage, right? So the distance here is let's see. So the same distance from the electric charge here, around here, the same distance from this electric charge will have the same electric potential, same voltage. And then away from it, you're gonna have another same. So if you draw a line that's same distance from the charge, then they're gonna have the same potential, same voltage. And you say that V1 is gonna be higher than V2. And this dashed line is called equipotential line. So the dashed line means along the dashed line, the voltage is constant. Voltage doesn't change along this dashed line. Same voltage all around it. Question. If I put the point test charge here, sorry. If I put the test charge here, if I put this little charge here, and then let's say if I move it along the equipotential line, it's the same voltage along it. Do I have a change in potential energy? Do I have any work done? Does this charge feel any force? Well, it has a force, but do you think that you're doing against the force or along with the force, or do you have any change in force? No. If you put the charge along, and if you're moving along the equipotential line, it's almost like you're rolling a ball on a flat surface. There's no change in potential energy because the voltage is the same. So there's no work done, no change in potential energy. All right. And then one thing, so you notice, is that equipotential line is always perpendicular to the field line. It's always going to be perpendicular to the field line because that's what it means, right? If you're moving along the field, then you have some force or that you have a change in potential energy. So all the equipotential line has to be perpendicular to the electric field lines. Let's look at the case that's minus Q. Minus Q, then you have a field line that's coming inward, right? Like that. Then again, the equipotential line for the minus Q, closer it is, it's going to be the least equipotential. But again, the equipotential line is going to be, and farther you go away, so it's more negative here, and then farther you go away, you're going to get more and more zero, bigger and bigger in value. So hope you understand that. I personally see these lines of a field lines and equipotential line like a topological map. imagine that like by having a positive Q, it's like the positive Q is going to be the top of the mountain. It's at the top of the mountain, and the bigger the charge is, you have a bigger, the steeper mountain, so it's taller, right? So then the top of the mountain, and then by having a negative Q creates the valley. It makes the valley. So somewhere here is going to be the sea level. This is the, let's say, the sea level, right? So what we're seeing is the side view. Side view. And for the, so that this is the height. So this green line, dash line, this dash line here shows the same height, same altitude. So same thing here too. It shows the same depth, how much lower you are, right? That you go closer to the negative, you go lower. The sea levels like deeper, right? And then you go above the ground, that you have a positive Q, you're making, you're going up as higher, you have the same altitude, and that same altitude is going to be the same equipotential line. And imagine that once you come here, this is going to feel the force, right? If you come here, this is going to feel the force that goes against it, along it. And then if you come over here, it feels the force that go along with it, that goes into this direction. And then what if you are bigger elephant, bigger particle? If you're bigger particle, then you have more potential energy. So the force will be bigger. You have a more potential energy, and the force will be bigger because your bigger particle means that you have a bigger charge, but the altitude, height doesn't change. So potential energy increases as you have a bigger charges that come by at this location, but the altitude is just created by the virtue of this, this big Q or this negative Q. Does that make sense? So the field, electric field or electric field lines, electric potential is only due to this positive Q or this negative Q. And it depends on what you bring, this Q naught or the big Q naught or small Q naught or positive or negative Q naught. They do different kind of work. They do possess different potential energy. They could have a different force, but the height or the field lines or potential is just wherever that depends on the charge configuration that's been there over there. So yeah, that's the idea. So the electric potential, the voltage is there just because of whatever that stuff is there. Another thing is that those balloon, I charged up with my hair that I showed you the demonstration, that balloon. That balloon, when I charge it up with my hair, you saw there's a repulsive force that's been created by having a two balloon that's charged. After the charge, after the friction, the balloon contains 5,000 volts. That balloon have 5,000 volts. Should we be worried of touching a balloon? It's 5,000 volts. No, I touched the balloon. You can touch the balloon. No biggie, right? But it has 5,000 volts. Even though it has a 5,000 volts, but charge that has is tiny. It doesn't have much charge. So it could be 5,000 volts, but for example, 1 coulomb is a lot of charge, right? So the electric potential is high, but electric potential energy, the work that it does, it may not be as much because you don't have much charge. So when you hear about the 5,000 volts, or it could be 100,000 volts, it's just a voltage. But how much work you do is the one that you need to worry about. So potential energy, the charge, is something that you need to worry about. Okay. The wall is 110 volts. You don't want to touch it because it contains a lot of electrons, right? Current. It possesses, because you want to supply all this electronic device, so it contains a lot of charge. So it has 110 volts. This is 1.5 volts. I'm touching it. I don't feel anything due to the resistance and stuff too. But that's not it's not 1.45 volts. That's not the reason why I can touch it. It's because the charges that it can do. Balloon is 5,000 volts. Let me show you another example. So there is something that's called Van de Graaff generator, and that can generate 100,000 volts. And then you're going to see, is it safe to touch the 100,000 volt Van de Graaff generator? So let me share this video, and then I'm gonna end my lecture with this video. So let's see. I wish I can do this with you, but I don't have a Van de Graaff generator. So okay, I hope you enjoy. He does a very good demonstration. So Van de Graaff generator generates over 100,000 volts. Hold on. Sorry. So you guys should answer all these questions too, please. Oh, drinking water. Insulator, right? So you guys should answer. Get his hair. 200,000. 200,000. 200,000. No force. I mean, no, you do have a force, but no work. 20. We haven't talked about it, but no much, no much charge. Lots of charge. So do a lot of work. All right, so that's the demonstration, and I'll see you in the discussion. This is the end of chapter 22. Hope you enjoyed it.